In this section, we're going to cover intermolecular forces. Now, intermolecular forces, first of all, I want to differentiate them from chemical bonds. So, chemical bonds involve the way that atoms in a molecule, in the same molecule, interact with each other. Of course, they're attracted to each other and they stick together. Intermolecular forces are not chemical bonds. So, they rather deal with the interactions between different molecules in the same substance. So, for instance, the interactions between two separate water molecules. And the strength of intermolecular forces, as we'll see, exhibits certain trends that are important to know. And they also have a lot of applications. So, just to remind you, because we are going to come back to these a little bit, there are three basic states of matter that we're concerned with. The first is gases, and then we also have liquids and solids, which those last two together are referred to as condensed phase matter. In gases, we have particles that are very far apart from each other compared to how they stack together in liquids and solids. There's basically no attractive forces between gas molecules, and they can move around essentially at random. Now, compare that to liquids where the particles are much closer together and they are very strongly attracted to each other. But in liquids, those molecules or particles, depending on what the substance is, are to a certain extent free to move past each other, which is why liquids can flow. In solids, we have a similar situation to liquids, except the particles are held in a very ordered arrangement as opposed to liquids where they can kind of slide past each other. Now, in terms of intermolecular forces, there's different types. So, one type, which we're not really going to cover, is ion dipole forces, and that's the type of intermolecular forces you get between two different compounds, specifically an ionic compound interacting with a polar covalent compound. We're not really going to concern ourselves with that. We're more interested in the intermolecular forces in single substances or pure substances. And these are van der Waals forces. There's three types of these: dipole-dipole forces, London dispersion forces, and hydrogen bonds. And I mentioned at the outset that intermolecular forces are not bonds, and so the name hydrogen bonds there, while that's an important concept, it's kind of an unfortunately named one because there's no actual chemical bonding going on. It's just another type of intermolecular force. So it's called hydrogen bonding, even though it's not actually bonding. Let's start with London dispersion forces. And the reason we're going to start with this is because all substances have London dispersion forces to varying extents. So unlike some of the other interactions we're going to look at later, which require certain specific substances to be present, all substances have London dispersion forces going for them. So London dispersion forces have to do with dipoles in molecules, but not in the same way that we've been discussing previously. In previous discussions, we talked about the dipoles that exist in molecules that are actually polar. Now, if we look at nonpolar molecules, those of course don't have overall molecular dipoles, but even in a substance that is nonpolar and even something that has nonpolar bonds, due to the nature of electrons, which is probabilistic, and so we can't sort of pin down their location at any given point in time, it's possible that in something that on average is nonpolar, we might at any given instant have a situation where the electrons are more dispersed towards one side of the molecule than the other. Even if, like I said, overall, averaged over time, we end up with a nonpolar molecule. So if we look at bromine, Br2 molecules with two bromine atoms attached together, those are completely nonpolar because we have two atoms of the same electronegativity attached to each other. Now, those are nonpolar on average, but it's possible at any given sort of split-second instant, the electrons in one bromine molecule might kind of shift to be biased towards one side of the molecule. So, for instance, that molecule on the left in the heat map diagram, the electrons might spontaneously happen to exist in a higher density on the left side of that molecule. If something like that happens, it actually induces other temporary dipoles in adjacent molecules. So if we get a spontaneous dipole in one molecule, a molecule that's adjacent to it, like say the one on the right, to its right, the electrons in that molecule will be attracted to the positive or partially positively charged end of the first bromine molecule. And so we get these interactions between the partial negative and partial positives that exist temporarily in these molecules. And due to that fact, these overall nonpolar molecules will have attractive forces between them. Now, London dispersion forces, being a type of intermolecular force, can dictate, the strength of intermolecular forces, but the strength of intermolecular forces has some implications for certain physical properties. So if we look at the four halogens, fluorine, chlorine, bromine, and iodine, which, when they're pure elements, exist as diatomic molecules. As you know from previous periodic trends, fluorine molecules are going to be smaller and way less than chlorine molecules, which are less so than bromine, which is less than iodine. And as molecules become larger and heavier, their dispersion forces are going to increase. As such, their intermolecular forces overall will also increase. And as intermolecular forces increase, both the melting and boiling points of a substance will also increase. So, for instance, if you look at the melting and boiling points for fluorine in this table, those are a lot lower than they are for any of the other halogens, because fluorine, being small and light compared to the other molecules, has lower London dispersion forces and therefore lower intermolecular forces. And as we go to larger and larger halogens, you can see both the melting and boiling points increase for all of those as we get to the larger and larger ones. Another factor that affects London dispersion forces is sort of the compactness of molecules. So here we have two examples of molecules with the same formula and therefore the same molecular weight. These both have the formula C5H12. On the left we have pentane, and on the right we have a compound with a different arrangement of carbon and hydrogen, but in the same amount, which is 2,2-dimethylpropane. Don't worry too much about where those names come from. The important thing to notice about those structures is with pentane, we have a longer and less compact molecule compared to 2,2-dimethylpropane. Now, both of those molecules are essentially completely nonpolar, and the only difference between them is how compact they are. So they have the exact same molecular weight and everything. And it turns out that if you have a less compact molecule, it's going to have stronger dispersion forces if everything else is equal. So pentane has stronger dispersion forces than 2,2-dimethylpropane, and therefore its boiling point happens to be about 25 degrees Celsius higher than the 2,2-dimethylpropane's boiling point. So that's London dispersion forces. Let's move on to dipole-dipole forces. These are interactions that occur not between spontaneous and temporary dipoles in substances, but in the actual permanent dipoles of polar molecules. So only polar molecules can have dipole-dipole forces between them. Now, polar molecules, being polar, necessarily have a partially positive and partially negative region of the molecule, and so they can have pretty strong attractions to other polar molecules if they kind of line up in the way that you see there on the left, where the partial positive end of one molecule is kind of surrounded by partial negative parts of other molecules and vice versa. So those attractive forces can be quite strong and influence physical properties like melting and boiling points. If we look at three molecules here that all have about the same molecular weight and similar sizes, the first one in this chart is propane. The next one below that, CH3OCH3, is dimethyl ether, and this third entry, CH3CN, is acetonitrile. So with propane, it basically has no dipole moment. It's just very slight. Dimethyl ether has a significantly higher dipole moment than that, and acetonitrile has a much larger dipole moment than either of the previous two. Now, because they're more or less the same weight and size, they have about the same amount of London dispersion forces, but the dipole-dipole interactions are much different between the three of them. So you can see the more polar the molecule, the higher its boiling point. And this is due to the fact that, for instance, acetonitrile is going to have much stronger dipole-dipole forces than something like, say, propane, which basically doesn't have any at all because it's nonpolar. And finally, we get to hydrogen bonding, which is kind of the last main intermolecular force that we'll describe. This one only occurs under very specific circumstances, so I want to be careful about how I discuss this. First of all, I just want to reiterate that hydrogen bonds, despite the name, are not actually bonds, they're just intermolecular forces between two different molecules. There's no actual covalent bonding between the hydrogens and the other atoms involved in hydrogen bonding. So hydrogen bonding occurs when we have a hydrogen atom that is directly covalently bonded to one of three other atoms. And the only three atoms that can qualify are oxygen, nitrogen, and fluorine, because they're basically the three most electronegative elements in the periodic table. So if a hydrogen atom is directly attached to one of those, it's going to have a very strong partial positive charge, because it's going to be a lot less electronegative than the atom that it's attached to. Now, it's also going to be the case that if a hydrogen atom is attached to one of those atoms, it's probably also going to have a lone pair. So the oxygen, nitrogen, or fluorine will probably have at least one other lone pair on it. And so, for instance, this happens quite a bit in water, where the hydrogen atoms on water molecules are very strongly partially positively charged, and they can interact with the strongly partially negatively charged oxygens on a separate water molecule, as you see there on the left. The actual hydrogen bonding interaction is shown in pink. And a similar thing can happen with ammonia, which has hydrogen directly bonded to nitrogen, another very strongly electronegative element. So the hydrogen has a strong partial positive charge, the nitrogen has a lone pair and a strong partial negative charge, and so the nitrogen on one ammonia molecule can interact very strongly with the hydrogen on a second ammonia molecule. Hydrogen bonding is responsible for some of the important properties of water. So, for instance, in liquid water, unlike most other liquids, the three-dimensional structure of the molecules is actually pretty ordered as opposed to being random. And so water has a number of unique properties that you'll mostly get into in Chem 1212, but chiefly this is due to the strength of the hydrogen bonding between the oxygens on one water molecule and the hydrogens on an adjacent water molecule. Hydrogen bonding is also important because it holds together the two separate strands of DNA, which is the biomolecule that contains the genetic information for all living organisms. So DNA consists of two parallel chains in a double helix, and each chain consists of DNA base pairs covalently bonded together, but then the interaction between the two separate chains is just due to hydrogen bonding. So hydrogen bonding is very important in biology for this reason, among many others. Hydrogen bonding is a pretty strong intermolecular interaction, and we can see this effect if we look at the table below. So it may not be immediately obvious what's going on here, but if you can understand this, it'll give you a really good idea of just how strong hydrogen bonding is. So what we're looking at is the boiling point of different substances. Specifically, in, say, this first cluster, substances that are covalent compounds formed between group 14, or 4A, elements with hydrogen. So for instance, elements in that group are carbon, silicon, germanium, and tin. So we have compounds like methane, CH4, silane, SiH4, and so on. And we can look at those and compare that trend with what we see in group 15, 16, and 17, or 5A, 6A, and 7A, where in group 15 we have nitrogen, phosphorus, arsenic, antimony, In group 16, oxygen, sulfur, and so on. And group 17, or 7A, are of course the halogens. Now, what you see in group 14 is more or less what you would expect before going over hydrogen bonding. As we get to larger and heavier elements combined with hydrogen, the boiling points increase because we have just larger and heavier molecules. So methane has a lower boiling point than silane, and so on. And if you look at the green, blue, and red bars in the other clusters, we see the same pattern. So for instance, in group 5A, PH3 has a lower boiling point than ASH3, which is lower than SBH3, and that's what you would predict. However, ammonia, which is highlighted there, NH3, if that followed the same pattern as group 14, you would expect to have a lower boiling point for ammonia than you would have for PH3. But it's actually not the case at all. In fact, ammonia has a higher boiling point than not only PH3, but also ASH3. And that's due to the fact that ammonia has really strong hydrogen bonds going for it. So there's really strong intermolecular interactions due specifically to hydrogen bonds. And you can see the same aberration with water compared to, say, H2S, H2SE, and H2TE, where water, despite being smaller and lighter than all of those molecules, has a much higher boiling point than any of them. Likewise, HF, hydrogen fluoride, has a much higher boiling point than HCl, HBr, or HI because of the hydrogen bonding interactions that are unique to HF within that group. So if we look at a comparison of some different intermolecular forces, again, we're not really going to talk about ion dipole. If we compare the strengths, London dispersion and dipole-dipole interactions are relatively weak, and hydrogen bonds tend to be quite strong in comparison. So you can see the values in kilojoules per mole there and some of the characteristics that are summarized in this table. So what we're going to do next is move on to a few examples, and I got these out of your book. So this is problem 8.88 out of the end of chapter 8, and it asks, what are the most important kinds of intermolecular forces present in each of the following substances? And it gives you 4 examples: chloroform, CHCl3, B, oxygen, O2, C, polyethylene, which is a hydrocarbon, which consists of carbon and hydrogen, and D, methanol, which is CH3OH. So what I'm going to do is give you the opportunity to try this on your own, and go ahead and pause the video, do that, and then we'll come back and actually go over the answers. Okay, hopefully you've gone over those. To understand what intermolecular forces are present in each of these, it's going to be helpful to know what the molecular structures look like so that we can tell, for instance, if they're polar or if they might contain hydrogen bonds. So for chloroform, that's going to look like this, where our central carbon atom is attached to a hydrogen and 3 chlorines. Like so. For oxygen, I should go ahead and draw in the lone pairs on those chlorines, just for the sake of completeness. For oxygen, we're going to end up with something like this, where we have a double bond between those and then 2 lone pairs per oxygen atom. For C, we have polyethylene. It's probably not worth drawing that because it's a polymer, which means that it consists of chains of hydrocarbons that are essentially infinitely long, so we'll kind of come back to that as we discuss that. And then for D, methanol, we have a carbon attached to 3 hydrogens and an oxygen, and that oxygen is also bonded to a hydrogen. So if we look at part A, chloroform, what are the most important kinds of intermolecular forces present in these substances? if we look at this substance, chloroform is going to be a polar molecule because the carbon-chlorine bonds they're all polar, and we don't have 4 of them, so they're not going to be able to all cancel each other. So there's a net dipole in this molecule that essentially points down. So this is a polar molecule, which means that it's going to have dipole-dipole interactions. Everything has London dispersion forces, and there's not going to be any hydrogen bonding here because we do have a hydrogen, but it's attached to a carbon, which is not nitrogen, oxygen, or fluorine. So for chloroform, we're going to have London dispersion forces, LDFs, and we're going to have dipole-dipole interactions, and London dispersion forces tend to be weaker than other types of intermolecular forces, so the dipole-dipole interactions will probably be the strongest. For oxygen, O2, this is a nonpolar molecule because we have 2 identical atoms attached to each other, and there's no hydrogens to speak of, so this only has London dispersion forces. So those are the only types of intermolecular interactions there, so those will be the most significant. For polyethylene, that's a compound of carbon and hydrogen. All of those are nonpolar, and they don't contain hydrogen attached to oxygen, nitrogen, or fluorine because none of those elements are present in that formula. So this again will only consist of London dispersion forces. And then finally for methanol, we have CH3OH. And the important thing about methanol is that it has a hydrogen that is attached directly to an oxygen. And when that's the case, that means that we can have hydrogen bonding interactions between 2 methanol molecules. So methanol, like all substances, will have London dispersion forces. The carbon-oxygen and hydrogen-oxygen bonds are both polar, because oxygen is much more electronegative than those. The oxygen also has 2 lone pairs that contribute to that. So it's going to be a polar molecule, so it will have dipole-dipole interactions. And more significantly than either of those 2 things, it also has this hydrogen directly attached to an oxygen, as seen here circled in green. So it also has hydrogen bonding, and whenever that's the case, that is always going to be the most significant type of intermolecular force. So those are the answers to problem 88. Let's look at one more example. And I'll walk you through this because I just want to use it to illustrate a quick point. In problem 94 here, out of the end of chapter 8, we have a sample that contains methylamine, formula CH3NH2, dissolved in water. So we're going to have water molecules and methylamine molecules in the sample. Which of the following illustrations depicts the hydrogen bonding that occurs between methylamine and water? So both of these substances have hydrogen atoms that are directly attached to some atom that can participate in hydrogen bonding. So in the case of water, we have our hydrogens directly attached to oxygen. In the case of methylamine, we have some hydrogens that are attached to nitrogen, which is another element that is eligible to have hydrogen bonding. So let's look at these possibilities and determine whether we have hydrogen bonding going on. So for A here, we have the lone pair on an oxygen, and it is shown interacting with the hydrogen on a methylamine molecule, so this might look promising so far. However, this hydrogen is directly attached to a carbon as opposed to a nitrogen. So while methylamine has hydrogens that can participate in hydrogen bonding, it's only these 2 that are directly attached to the nitrogen that can do that. This first hydrogen right here is not all that partially positive because it's attached to carbon, which is an element with a similar electronegativity to hydrogen. So part A here is not how this hydrogen bonding takes place. If we look at part B next, we have an interaction between the lone pair on the oxygen of a water molecule, right here, and it's interacting with a hydrogen, and this hydrogen is directly attached to a nitrogen, which is one of those atoms that makes it eligible to be very partially positive, and so it can participate in hydrogen bonding. So B does show a correct hydrogen bonding interaction. Let's go to C next. In C, we have the lone pair on this nitrogen and methylamine, and it's shown interacting with the hydrogen on a water molecule. And that hydrogen will be strongly partially positive because it is attached to an oxygen. So the lone pair on a nitrogen, nitrogen is one component of hydrogen bonding, and this hydrogen on this water molecule is also capable of doing hydrogen bonding because it's very strongly partially positive, being attached to an oxygen. So C is also a valid hydrogen bonding interaction. Finally, if we look at part D, our interaction is shown between two hydrogens. And remember, a hydrogen bonding intermolecular interaction needs to take place between a hydrogen on one end, but also a lone pair on the other end. So these are actually both partially positive because both of these hydrogens are attached directly to very electronegative elements. So this is actually not a very favorable interaction at all. So this is not a hydrogen bonding interaction. Okay, so this brings us to the end of Chapter 8. So I'll go ahead and stop there, and please contact me during office hours if you have any questions you want to go over anything in these lecture slides. Thank you.